Toplanan ve geri dönüştürülen plastik gıda ambalajı tasarruflu bir ampule dönüşerek yeni bir enerji kaynağı olabiliyor. PAGEV, plastik sektörünün birleştirici gücü.
Well, we'll wait a few minutes till everybody shows up, or just a couple of minutes, and then we'll start. Okay, can you put the? Oh, you put the video first. Video. Okay, video. Okay.
Video for people to.
Yeah.
I have one question.
Yes.
Toplanan ve geri dönüştürülen boş gıda ambalajı pratik bir ürüne dönüştürülebiliyor. Böylece plastik atık günlük hayatta ihtiyaç duyduğumuz yeni bir ürün olabiliyor. PAGEV, plastik sektörünün birleştirici gücü.
Okay. No, we have finished. We take the second one. This is the second video,
You want video or presentation?
No, the presentation. Extruders, yes. Okay, super. Great. Okay, thank you. I thought I know how to say Turkish good afternoon, but I forgot. No, geceler is after evening. How do you say good afternoon, or you say geceler? No. Geceler. Good night. How is it for this time of the afternoon? What would you say? Günaydın. Oh, it's Günaydın. Okay. All right. Good. I know. I learned something. Okay. Good afternoon. Anyway, we're going to talk about extruders, about screws and dies, and we're going to start from the analysis of a single screw extruder. Options that we have between the grooved feed extruder, smooth, differences between screws for injection molding and extrusion. There's some differences, and then extrusion die design. I'm going to be sitting down. Just standing up is just tiring a little bit. Standing up all the time. The sort of screw extrusion is frequently attributed to Archimedes, but Egyptians actually had screw machines before Archimedes. So it really goes back many years. In terms of technology, it happened in the 1950s. There was a group at DuPont, and among them it was McKelvey, James McKelvey, who was in fact the Dean of Engineering at my university in the United States, Washington University, when I was a student. And there were some other people very clever and very capable, and managed to produce a series of papers that were published around 1953. And this is what I knew about sort of the history of scientific approach to extrusion. However, in one of the short courses I give, and I've given 78 short courses around the world, and one of them told me about Maillefer. Some of you may know about Maillefer screw, and I'm going to show you later. But Maillefer is a company based in Switzerland, which was formed by Maillefer himself. And I had few people over the years to take my course from this company, and they sent me the doctoral thesis of Dr. Maillefer, the founder of the company, which was done at EPFL, the Technical University in Lausanne, Switzerland. And to my surprise, to very great surprise of mine, Maillefer and the DuPont team had very similar flow analysis, to my very great surprise. I did not know they were produced at the same time, and I do not think they knew of each other's work. So I give credit both to the DuPont team and to Maillefer at the same time. Now, one thing that we should really understand in this case is what happens and how we are going to form a melt pump for molten polymers. Now, we know how pumps work, you know, the centrifugal pumps that you have, let us say, in this hotel and everywhere else. You know, you have the rotation, and because of the Bernoulli effect, you have high speed and so forth. It really works, a centrifugal pump works because of the Bernoulli effect, in which case you have pressure built up due to momentum, due to inertia forces and pressure forces. However, for molten polymer flows, there's no inertia because we have very, very high viscosity. We don't have very much of inertia at all. And the operation is really entirely different, as you will see. So we're going to build up a pump, and here I have a first sketch. You know, this one, so you move the top plate, the velocity there is equal to the velocity of the plate. Down here is 0, so that this kind of contraption does move a liquid. And I've seen such a pump. It was in a metallurgical plant. They were just moving some kind of polluted water, heavy with some kind of mud. And you don't really see that often this kind of pump. Now, if we put an obstruction at the end, of course, we're going to have some backflow, and at the same time, we're going to have some buildup of pressure. This is, if you're a mechanical engineer, you might have heard of the Rayleigh step, that you build up pressure and so forth. It's been discussed in fluid mechanics books. Now, okay, this is 100% pump because it builds pressure and moves a liquid. So it qualifies as a pump. How can I convert this simple thought experiment into a practical device? Okay, we'll do that. This picture, I have borrowed it from the book of Zev Tadmor and Kostas Gogos on principles of polymer processing. And they say, okay, let's see how we can do it. Right here, we have a device, we have some kind of a shallow vessel, and on top of it, we move a plate. Well, this is not very practical, you know, you're not going to be, because this is sort of, you have this vessel, you move a plate on the top because of the drag flow principle that I just showed you, and of course we have obstruction over there, it would be a pump. It's not a practical thing. Well, what we can do, we can twist the rectangular sort of vessel, if you wish, wrap around the plate, so we end up with a screw in which essentially we rotate the barrel and the screw is stationary. So that contraption, sort of twisting it, wrapping it around, you form a pump. In fact, for the analysis of a single screw extruder, we're going to use this principle. We're going to have a stationary screw and a rotating barrel. All right? Now, there are some people, many of you may know Greg Campbell. He comes to the PPS meetings. Okay. Some people say, it is Greg Campbell is one of them, that rotating the barrel and rotating the screw is not 100% identical. He's got some arguments. The result is that if the barrel, if the screw is shallow, has shallow channels, there's not really much of an effect. If it's a very deep screw, yes, there is an effect. But in extruders, the channel is shallow. It's not very deep. So that there's no question that the approximation, which I'm going to be using here, and I'm also using it in my software, of rotating barrel, stationary screw, is really valid. But there is a point that if it's a deep channel screw, very deep, there might be some differences. So, okay, we managed to do a thought experiment, what Einstein used to say in German, Gedanken experiment, those of you that speak German. It's a thought experiment. We managed to form a device that could operate as a melt pump. But of course, you know that extruders are more than a melt pump. You supply, as you can see over there, the pellets, and the pellets get melted. First they get transported, they get melted, and eventually they get pumped. So the melt pump analysis is really valid only for this last section right here. Whereas the question is, how do molten pellets get transported forward? Well, I'll show you. This is my own fingers out there. I took a picture. And I have as you can see, a screw and a bolt. Right? Now, the bolt corresponds to the solid bed of pellets. All right? How am I going to move it forward? Now, if my hands are oily, right, I don't think I'm going to be able to move the bolt at all. Also, if the screw is corroded, it's not moving. So, in order to move the bolt, I must have a very clean screw, and my hands, my fingers, must not be very oily or no oil at all, right? Which means that I have to have more friction on the tip of my fingers than on the screw. And this is the principle. In order for an extruder to operate and be capable of moving solid pellets forward, the friction coefficient between the solid pellets and the barrel must be higher than the friction coefficient between the solid pellets and the screw. Typically, in fact, this will give you, there's some, I've written a couple of papers myself, other people have written more papers, and you see that this kind of mechanism with friction gives you an exponential pressure buildup. I mean, this, when you turn the screw, right, you build up a lot of pressure in a very, very short time. In a very short. How do I measure the friction coefficient? Well, friction coefficient, if I wanted to measure on this table, maybe I can have a weight and pull it. The friction coefficient on this ground, it's marble. I see. My estimate is less than 0.4. It's a bit, which means in order, let us say, you need 40% of my weight to pull me forward, right? The friction coefficient in North America, because North America, in particular United States, when you place a floor anywhere, the lowest friction coefficient allowed formally is 0.4 between shoe, typical shoe, and the ground. Now, this one is on the a bit higher, and if somebody fell, you know, the company, the hotel is a bit responsible, you know, and I have worked on a couple of cases as a consultant, like somebody fell and money is big. So it's about 0.4. Well, on the barrel, the friction coefficient should be at least 0.4. On the screw must be shiny. Low friction coefficient should be about 2.5. So, I mean, 0.25, all right? So these are the ranges of friction coefficients that we like to have, as I have it over there. So this is shown that on the barrel, we like to have a coefficient 0.4, and on the screw about 2.5. So these are default values. I have a software package, which I sell commercially, and I have default values for smooth barrel and a typical screw, 0.4 and 2.5, in order for the extruder to function in a normal way. Now, if I have a screw that is corroded, damaged, obviously 0.25 is going to go up, and it may not produce. And I'm going to show you later on some screws in pretty bad shape, okay? And so I say the same thing again, solid bed, barrel, it would have to have 0.4 and the screw 0.25. And typically then the pressure variation along the screw will be of that shape. This screw in that particular case is going to be a gradual build-up. Here we are compressing. There's going to be, you see, this is the typical design of a screw. It's a straight portion. We do the feeding right here. Then it's compression. Compression will give some kind of pressure rise because you're compressing it. And then you have a straight portion, which is the metering section. And then, of course, you have a large pressure drop in the die. So this is what you get. However, I mentioned that I need at least a friction coefficient on the barrel, 0.4. How about if I make it larger, intentionally? All right? How can I do it? Well, I produce the grooved feed extruder. So I put grooves on the extruder. The grooves are of different shapes, but this is the most prevalent. Rectangular grooves is the most common. The other ones, I don't really see it. I just have it really for, you know, somebody may want to do it, but this is the standard kind of grooves. The length of the grooves is not very long. It's only L/D about 4, no more. But you built a lot of pressure, a lot of pressure. That's the way the pressure is. The pressure right at the start, you built a lot of pressure, which will probably be at least 150 megapascals. In the die, most we can have is about 50 megapascals in the die. But this one, I have seen measurements. I'm not sure if they're measurements or calculations. This is very difficult to measure. I've seen up to 30 megapascals of pressure built up. So the pressure is very large. And the pressure is very large, and you may really have problems, you know, and it's rather difficult to design groove fit extruders. Everybody can design and build smooth barrel extruders. It's not a complicated machine. You can buy screw from somebody or design it and fabricate it yourselves. But when it comes to groove-feed extruders, it's complicated. Yes, in Turkey, I know and I have contacts with one company that they produce groove-feed extruders. They're very good. They pump out a lot of material because, why? You really have built up of a lot of pressure. So that this pressure that you build up, we're talking about 150, 200, this pressure is building up and is pushing the polymer out, you know. So, and in this case, check the previous shape. Look at this. Right here, we have compression in the screw, right? The compression ratio is usually around 3, between 2 and 4. That is the gap here over the gap there is about 3, let us say, between 2 and 4. And the pressure, maximum pressure there may go 60, 70 or whatever. Anything beyond that is probably too much. However, in the grooved feed extruder, we have at the start, we have 150 at least, and probably 200 and so forth, that is pushing the polymer. And right here, this screw does not need any compression. It's practically one. You know, there is a little bit in this one, either no compression or 1.2 or something like that. Just a little bit of compression. So there's a fundamental difference between screws for groove feed and screws for smooth barrel extruders. And the difference is that the pressure that develop is very large. Now, do you see any problems? And I'll tell you what the problems are. Do you see any problems, potential problems, with groove feed extruders? What sort of? Say that? EVA? Well, grooved barrel extruders are not designed. You don't want very hard or very soft polymers to, first of all, because the pellets will go into the grooves, number one. Any other problems? Where? Okay, where? Temperature control, not so much. Actually, the groove feed extruder is pumping out more material, and the temperature normally is going to be lower, generally speaking.
If screw is not a suitable design, melting and mixing problems.
Okay, the suitable design, right? Okay, suitable design. What about problems with the size or the shape of the pellets?
It's also important for the designing the grooves.
The grooves, okay. Okay, this is really the point. You have to have very nice pellets, like preferably virgin material. If you have regrind, you know, and let us say you have an operation and you take regrind and you put it in. The size of the regrind, right, which is granulate, and the virgin pellets that you put there is not the same. They do not go very nicely into the grooves, and this can create problem. Like, if you use regrind, most likely you're going to have problems. If you use recycle, well, it would depend. If you have nice pellets, you take the pellets, you regrind them, you have nice pellets, and then you put them in a groove feed extruder. Now, the big advantage of the groove feed extruder is high output. Like, how high? Double. You double the output. Well, if the polymer is too soft, it's not suitable. If you have flakes, you want a pellet that is hard but not super hard, you know. You want, for Hdpe, it works very well. Polypropylene works very well. If you get something like polycarbonate, I doubt it would work. Soft grooves. What kind of soft grooves are you thinking about it?
Soft groove and hard groove feeding. They separate in two in the articles which we read. Yeah, there is another idea which say there are soft grooves and hard grooves. Soft grooves makes easy to feed also some flakes as well.
Generally, the feed material can be problematic. How you, what kind of material you feed and so forth. But they work very well, you know. And if you have good pellets, but with other stuff, sure, it may work, you know. But my experience is that I would recommend grooved feed extruders for good material, good pellets. I would not recommend it for recycle, except if recycled polymers are converted to good pellets. I would not recommend it when you mix virgin polymer and recycle together. You see, because the virgin polymer would have nice pellets, 3 millimeters in diameter. The recycled would be probably cut up like you extrude, and then you chop it up, and you have irregular shape. Irregular shape generally is troublesome, but who knows? And somebody can come up with another design, another innovation that make it work. But these extruders are small, and I have seen extruders pumping out a lot of polymer, and I see small extruders pumping out, wow, you know, an awful lot of polymer out. And I say I know of at least one Turkish company. They do very good extruders. Yeah. Melting. Melting in extruders started to really become understood after the work of Bruce Maddock, who was working at Union Carbide. And he did a extrusion experiment. He stopped the extruder, then pulled out the screw and looked at what happened. And he came up with this model. Like, the die is in that direction, that way, and here is the feed on that side. And the solid bed, at least ideally, segregates in that sort of flight. Then the melting occurs in a thin film between the barrel and the solid bed, and here you have the accumulation of the melt. So that's the standard way of doing melting. And here I have sketch, and you can see the sequence of solid bed transport. Right here, you have a small melt pool. The melt pool is increasing, and so forth. However, you do not you do not like the breakup of the solid bed. Because for melting to occur, I do need shearing of the solid bed against the wall. Now, if I have broken up particles like this sketch like this, they do not melt. And if they do not melt, they're going to end up in the extrudate. And I'm going to show you results. I have actual experiments that I'll show you. And this is bad news. So we don't want this to happen, you know, because these particles, they float in the melt, and they just never melt. So you really need shear in order to be an effective melting machine. Well, the melt pumping then is what I mentioned. You have a little bit of trigonometry to deal with, but essentially it's drag flow. Like you move, I move the barrel, but I do not move the barrel in one direction, because I move the barrel and it goes in the direction of the helix. And so they are simple equations, and you will see the derivation in my book, which has been sent to you, and I say the output, the flow rate that we get, is determined by the drag flow minus the pressure head minus any leakage that you may have between the screw, the flight, and the barrel. These equations are derived in the book, and in the case of grooved feed extruders, we may go from 50% to perhaps double the output rate for the same diameter and the same speed revolutions per minute. So you will see the details of the derivation, and I have a detailed example over there. Now, the flow within the channel of the barrel is like a helix within a helix, because as the barrel moves, the barrel sort of be moving in this, moving down, so that it drags the polymer down, it hits the wall, nowhere to go, it goes back, and it comes back again, goes back, so that the flow of the polymer within the channel, because of the helical geometry, it's a helix within the helix of the channel. So it contributes somewhat to the distributive mixing. All right? It's a helix within a helix. And so again, I show you another picture of how we calculate the output. And the output is really calculated. Essentially, if you have drag flow, you have that. If you have drag flow assisted by the high pressure in the groove feed, you're going to have more flow, right? So it gives you that kind of a profile. However, if you have drag flow, which is prevented from coming out due to the pressure of the die, you're going to have some backflow. And these are the equations essentially we use in order to develop a model. Now, this equation is the so-called drag flow equation. How much polymer can you get from a smooth barrel extruder? Use it. For a smooth barrel extruder, I'm willing to bet right now, any extruder, in any company, if it's a smooth barrel extruder, this equation will give you within 25%, this is the output. Very simple equation, right? You'll get the output. If it's less than that, the first thing, whenever I'm asked to inspect an extruder and there is some trouble, I just check the output against this equation. If it's less than that, there's some trouble in the extruder. What? Maybe screw is corroded. Maybe barrel is corroded or damaged, right? Something happens. If it is grooved, of course, you can get double, you know? So the question you're going to ask, is it grooved feed or is smooth barrel throughout? You know, these are two questions. Now, groove feed extruders were invented at the University of Aachen in the 80s. In the United States and Canada, they had a very, very slow acceptance, very, very slow acceptance. I remember I was in Germany, I had spent some time in Germany, I went back to Canada and I tried to convince a couple of people to do research, and I was told, well, why bother? Use a ½ an inch larger diameter. You get the same output, you know, end of conversation. That was then. Now, they are used more frequently, but still, they are not used that much. I mean, in the United States and Canada, I don't really see too many groove feed extruders. I don't see them. In Germany, also in Turkey, throughout Europe, I see them in South America. In fact, I know in one installation through my customer from Canada, the customer in South America obtained an extruder, groove feed extruder from Turkey. Two of them, actually. They told that's what they wanted, and they're happy with them. So, something to think about. But this equation, I urge you to use this equation whenever you want to do any calculations. And I have a very detailed example in the book. The example itself is a very simple example, but it goes over at least 10 pages. I calculate the power, the torque, the output, pressure generated by different methods, and I compare the calculations against my software. In all of them, it's amazing how much you can do with very, very simple equations. So I do urge you to use that example if you really want to learn about extruders, especially if anybody from a university, I would certainly recommend it very much. Now, well, how about if we groove the entire barrel, not just the feed? That's the latest trend, is to groove the entire barrel. And one of the major proponents is a good friend of mine. He's German. And if you go to the K show, there is going to be a stand there of Helibar and so forth. They have some small extruders, not very big diameter, but the entire barrel is grooved. There have been a couple of publications. I have, okay, there is at Antec and also SPE, International Polymer Processing Journal. You're going to see the information. He tells me, and other people tell me, that with the entire barrel grooved, you can quadruple 4 times, that is, the output of an extruder. And he's certainly doing it. And these extruders, they work at very, very high speed. We're talking about 1,000 RPM, all right? 1,000 RPM. And I think I have some results to show you later on. The Helibar extruder, which is built by my good friend Eber Grinslös, whom I know from the 70s when I was at the University of Stuttgart. He's got a couple of papers, you can read them. And if you go to the K show in Düsseldorf in October this year, I think it's a good idea to visit the booth. I think it's a company called Extruder Technique is the name of the company, and Helibar is the technology. And this is from Grinslös and shows the difference between a conventional grooved feed extruder that you build up the pressure very, very high in a very small region, like which is going to have, of course, wear, as you said, you know, like it's a tough region. And, it does appear, actually, it's not only you think about it, I've seen it happening, you know, that region of very high pressure, if things happen, like pressures are enormous. In his case, he claims at least that the entire barrel is grooved, the pressure is more gradual, and eventually he gets higher output. To tell you the truth, I'm not quite sure how it works. The analysis is not exactly clear why it works, but I'm just presenting you the results as I see it. There have been contributions of very high speed single screw extrusion by Wortberg. There have been by Battenfeld, Cincinnati, and there are some people, some of you may know the names of John Cristiano and others. And reports, Cristiano reports from a 63.5 millimeter, that is 2.5 inch extruder. At 1200 RPM, you get 1400 kilograms an hour, which is a lot, you know. I mean, from that kind, but there are reports, there are references, and you can check it for yourself. This is some result, again, from Cristiano, from Antec, as you can see, what kind of outputs you get with this kind of high-speed machines. L over D is rather large, but you get, you see, 1400 for that kind of material, 1200, you know, it's a lot of output. Now, the same thing is shown from Battenfeld, Cincinnati, which is a very well-known German company. I know they sell a lot of extruders. Also in Turkey, I know they sell extruders. And as you can see, you get a lot of output, although they did not specify. This is from a plastic pipes conference in Berlin in 2016. I attended, and I have the proceedings, and you can see sort of what sort of outputs and temperatures you get. But they don't say the screw RPM is normalized, I guess, for reasons of proprietary knowledge. They do not disclose it. The problem I had with these extruders, they are fine machines, great output. The problem I have is mixing. You see, you pump out a lot of material, but I told you this morning that mixing is very, very important. To start with, any extruder, whether it's slow, whether it is fast, it is not a very good mixing machine. Although you see things rotating and whatever, you add a Maddock dispersive mixer, but it's not a very good mixing machine. And if you really want to do mixing, good mixing, you need co-rotating, twin screw extruders with wide discs. All right, what I showed this morning. Well, with extruders, single screw extruders, mixing is never very good. But when you have also high outputs, it might be worse, okay? And in some people, I told them to, you may not need the output. You see, like I've been in extruder plants where they had high output, high speed, but they didn't really need it. They needed quality. So something to think about when you buy or when you inspect an extruder plant. Now, for power requirements, the calculations are rather simple. What we want to do is we can calculate the power that is inputted by the screw by determining the temperature required for the polymer to be raised, the energy required for the temperature to be raised from room temperature to, let us say, the extrusion temperature of 250 degrees, the temperature required to melt the polymer, which means the temperature that we have to supply the polymer with to overcome the heat of fusion, okay, which is the opposite of heat of crystallization, and the energy required to pump the polymer. Here I do some calculations, and from the calculations, which are explained after that, you will see that most of the energy inputted by the screw, so the rotating screw is what melts the polymer. The heater bands, they only contribute a small amount. Most of the energy, 80% of the energy, is coming from the rotating screw. You see? The heater bands, they may contribute perhaps 20%, maybe 25%, no more than that, So, and then if you look at the numbers, how these numbers go, you'll see that most of the energy is going to raise the temperature, to a lesser extent to melt it, and then for pumping is not very much, which means that the extruder is not an efficient pump. Now I have a few things about terminology here. I will not say very much. I already said it. After that, I'm talking about general purpose extrusion screws. I give you actual numbers. If you want to check against any particular designs, if you want to start compression ratios for Hdpe, probably 3, 3.5. Polypropylene 3 to 4. If it's something like PVC cannot take high compression ratios. You probably go around 2, 2.5, and different recommendations. There's nothing very much to say. The differences between screws in extrusion and injection molding, generally screws used in injection molding, they are shorter. In extrusion, we need the extra length because we have to build pressure, and we build the pressure by the long metering section, which is not the case. So generally speaking, injection molding screws are less sophisticated. They're simpler. However, they're getting improved in recent days. I have some numbers there for you to look. Helix angle. There are some recommendations from BASF. Again, these are numbers for you to look at. If you're at a university, you may want to give it to a student for a screw design and so forth. Now we come to a very, very important subject. After groove feed, the most important subject is the question of barrier screws. What is a barrier screw? Well, first of all, it's not a double-flighted screw. Like barrier screw, we are going to have a main flight and a secondary flight. It is also possible to have a double-flighted screw. Like you see, you have one screw and then we have a second. Well, this is a screw design, but it's not a barrier screw design. Read my lecture note, my book, to see more information about this, why they might be sometimes beneficial. Now, how was the screw design was developed? You see, we have this kind of melting mechanism from Bruce Maddock. You see that we separate the solid bed from the melt pool. Well, what about if we actually put another screw right there, right? Where the solid bed ends, we put another screw, a barrier screw, to separate the solids from the melt pool. That's the basic principle. But this basic principle, of course, has generated a lot of designs. Okay, this is the screw without a barrier. Okay, and what I pointed out already is that if in the channel I have unmolted pellets or chunks of material that have not been melted, they just float, or I may say swim. They swim really in the melt. They are not likely to get melted. So it is better to squeeze them, to force them against the barrel. And this is the birth of the barrier screw. You see, now I have the previous geometry that I segregate now the solid bed from the melt pool. I segregate the solid bed from the melt pool, you see? And eventually I only have 100% melt. So this is a better melting machine, all right? This is a sketch closer to a mechanical design as it was invented by Maillefer probably around 1960. And you see, you have the main flight, right? Main flight, and you have the barrier flight. So in this section, you would have solids, and right here, you would have melt. And so that the solids part becomes smaller, and the melt becomes bigger, and hopefully, so this is more difficult to design, because how do you know whether solids have been melted and how much? You know, this is tougher to design. But they work very well. And I would say that most of the modern screw designs are of this variety. That is, they are barrier screws, and they are different. A lot of patents out there. This is over there on the top. It is referred to as the MC3 or Hdpe screw, whatever. It is really the Maillefer screw. This is another one, and this is the bar 2 screw, in which case you can change either the depth or the width of the channels. In the Maillefer case, the width is changing In the other one, the width is remaining the same. So there are a lot of different designs. You will find some references in my book, but there are different designs that work very well, and most likely, any modern screw that you see anywhere is going to be of the barrier variety, like this. So, but generally speaking, it's more difficult to design them, you know. And I do have a software package, and I use it, and it is used in industry to do it. Mixing sections. Well, I think I've already mentioned to you that single screw extruders are mostly melting and melt pumping machines. There is no dispersive mixing, really. I mean, in the barrel, what I'm doing is shearing all the way. It's really shearing all the way through. So it makes sense to add a mixing section. The most, perhaps common and most successful mixing section is the one that has been proposed by Maddock. It's the same guy, Bruce Maddock, that proposed did the experiments on mixing. And this one, what happens is that the polymer gets in there, and here it has something like a barrier, which is forcing the polymer to travel over this barrier, if you wish, to the next channel. And here is the view on the other side. And then this is another picture. And actually, I have this picture from Bruce Maddock himself. He gave a talk a few years ago. And you see inside the channel, you do have some circulation, which is a good thing for distributive mixing. And over this barrier, as it goes over the barrier, you see the polymer in this region is being squeezed, which means the flow is elongational. That is why these mixers are referred to as dispersive mixers, like Maddock, and there are other variations. In fact, this mixer, this so-called Egan mixer, again is distributed and dispersive. Again, you're forcing the polymer to go over. You see, you have the polymer there. Now it is slanted, it's not like a barrier, but you're forcing it to go over this barrier to the next channel. And some people think that this one, the Egan, is a little bit better than the traditional Maddock mixer. Now, a mixer like that, which I see them very frequently, this is a pin mixing section. Well, the pin mixer has no elongation of flow regions. They are really used for dispersive mixing. They do a good job for dispersive mixing, but that's about it. Well, they do a job, but do not expect that this is, I have to remain that because I gave mentioned something this morning about a customer of mine. He was mixing polypropylene and Hdpe. All right? He wanted to make ropes. The screw had only such a mixer, pin mixer. When I saw that, I said, send me a picture. I wasn't near the plant. I said, send me a picture of the screw. When I saw this picture of the screw, I said, well, where do you do any dispersive mixing? Nowhere. It was a regular screw with a pin mixer. Nowhere elongation flow. The Hdpe and the polypropylene could not be mixed. All right? And he had the problems they had. And after they were replaced, they replaced the screws with better screws. The problems went away. Extruded surging. Well, we presented the analysis, different types, and now I want to discuss some of the problems that we have with extruders and do some. And one of the problems is extruded surging. Usually, extruded surging originates in the feed section, usually. Maybe in the solids, well, feeder, solids transport, melting, everywhere, but mainly at the start. And I have here an analysis of sort of how to do a systematic troubleshooting. And you suspect the feed if you have powder, fluff, regrind, moisture, and so forth. Maybe I'll take just one of them. I'll tell you the story of this one to appreciate the problem in a mixing problem. Now, I was asked by a manufacturer of catheters for their small diameter tubing used for angioplasty. They put it from here up to the heart or from down below, goes to the heart, and they blow a balloon, you know. And typically, these are small diameter tubes, a little more than 1 millimeter in diameter. Very small extruder, you know. And they told me that they had very bad surging. And I did go there, and it was the best or the worst, depends which way you look at it, surging that I have ever seen. It was a small extruder, maybe 1 inch diameter, slow moving, and the fluctuations of pressure and output were huge. I remember the pressure just going up and down. I mean, I wish I had such an extruder in my university laboratory to demonstrate to the students, because I'm talking to them about surging, but I was never able to reproduce surging in my lab using Hdpe. Now, they were using a polymer which is called PBAX. It's a standard material for these kinds of catheters. This is like nylon type of material, and it's hydroscopic, okay? And hydroscopic needs to be dried very, very well, okay? I asked them about drying. Yes, we dried it, no problem. Well, the problem was difficult. They asked me to design a screw. I checked the screw they had. I could not design anything better. We ended up being 4 consultants there. I was the academic, and the others had practical experience. We could not solve it. How did I solve the problem? Well, I took a few grams of the polymer PBAX with me, and we put it in the oven in the university laboratory. Then I asked my technician there, you know, how long it took. to get rid of the moisture. And she told me it took about 8 hours, just in laboratory oven, you know. I asked those guys, they told me, oh, they only dry for 2 hours. Well, it wasn't enough. You know, that was the problem. Moisture, what happens with moisture? Back to the original picture, of my fingers, right? The screw and the barrel. What happened was moisture went between the solid bed and the barrel. Just if I throw a little bit of water, you know, on this floor, it's difficult to walk. The friction coefficient dropped to very little, and it was sometimes biting, because it grabs it, and then you push it out, and sometimes nothing, and then fluctuations galore. You know, I was never able to replicate this experiment in my own lab to show it to my students, because I would give them lectures on extrusion surging. So solids conveying, I did say that. Surging and melting, you may have it. Well, oh, here I have the entire, well, this is the surging extrusion of P-bags that I mentioned already. Another problem is screw and barrel wear. Well, soft polymer can do a lot of damage to a very hard, very tough steel like this. This is from an actual picture from one of my consulting business. What happened is, in this case, you see, what happens in this case is that this screw, the flight, was pushed against the barrel, and you see something is cut off from here. Now, these pieces of metal, they go inside, and of course they scratch the surface of the screw. And of course the customer is complaining. He says, well, we don't get output, poor performance. Well, what do you expect? Now, why does this happen? It's a classical case of bed wedging, like a wedge. What is wedging? Well, you know that. This is a typical homework assignment that I did in high school. You put a wedge here, and you force it down, and you can lift with a wedge a lot of weight. Same thing happens in the screw. A little bit of solid polymer gets somewhere on the screw, pushes one side of the screw against the wall. It doesn't take very much. You see, let's this one with 1 kilogram force. This is typical high school or first year mechanics problem. You put with 1 kilogram, you can lift 1,000 kilograms, so that you bend the screw. Bed wedging means you turn around, you generate a little bit of screw, a little bit of force, right? It pushes the screw against the barrel, right? The barrel, the flights get damaged, the damaged pieces fall into the screw, and you see the outcome. And this is a picture somebody by from, what's his name? Franklin, Jim Franklin, I think. I know this guy. And we have a pressure area, in this case, that causes a lot of damage. So bed wedging can be a problem, because once you have bed wedging, you're going to have surging, you're going to have serious damage, and something to worry about. Jim Franklin did some calculations. I'm not sure how measured or did, But anyway, my calculations from a simpler experiment of bed wedging with first year university mechanics gave me pretty much the same results. Occasionally, there's melt blockage. All of a sudden, you run the extruder, nothing comes out. And I gave a course, a short course, last week in Brussels, Belgium, and I asked the class, I had 22 people from industry there, and they told me, a couple of them told me, yes, they have seen this phenomenon for various reasons. You know, maybe something happened with the, maybe moisture, maybe with, it happens in the solids conveying zone, that all of a sudden the thing is rotating and it slips without anything being pumped out. Moisture, I did mention. Whenever you have temperature sensitive materials, be careful because of the problems that I mentioned, and you really should check the function of the dryer, but also ask the supplier of the resin. The supplier of the resin may have some good advice for you, like how long would you have to dry the material, or ask for advice from the supplier of the drying machine. You know, what do they say? And so useful information that you may gather. Moisture is a big problem, and it can create a lot of other problems. Another problem is gels. Now, gels in polymer science are cross-linked, really, polymers. But in extrusion, anything that is visible to the naked eye, could be dirt, it could be unmelts, it could be anything else, it is referred to as gels. Might not be a real gel, all right? So the first thing you have to do is, if you hear about a gel, is it a real gel, 3D, cross-linked, or is it just an unmelt? The way we do it, we take a film normally, put it in the oven, raise the temperature. If we see that we go, let us say, for Hdpe above 140, whatever, and it melts, well, this is not a real gel. It's probably unmelts, and the unmelts cause the trouble. It could be some form of degradation. And one of the, so the gel, of course, you may have paid for it actually, because when the resin producer is producing the resin, well, the vessels, the reactors are not 100% clean. They have something from a previous product. And when they have a frequent changeover, normally you get gels, or depending on the catalyst and so forth. I remember I was in a blown film production facility, and they had some kind of optical device to measure gels. It would shine a light into a square of about, it wasn't very big, maybe 20 centimeters by 20 centimeters, 20 centimeters, and it would count the gels. And you could see it was giving a sound. It would be like a Geiger gauge, you know, detecting nuclear material or something. Continuously, you would hear it. In my guess in that case was that it was probably purchased. They had paid, you know, when the supplier gave them the resin, it was already there. But you might have generation of gels or some form of degraded materials right in the screw. Now, we frequently recommend that this kind of screw with sharp corner like this should not be used. It is better to have a rather wide angle right here. And what happens in those cases, both on one side and the other side of the screw flight, you have the generation of gels. And in fact, I did some computer simulation, and in the extruder, with the geometry of the extruder and real viscosity of the extruder, we see the formation of vortices. This is known as Moffat vortices. They form on both sides of the screw channel, and this is the side. And this one, for example, to travel, for the polymer to travel just one diameter, it takes something like minutes, you know, whereas the average residence time distribution in the extruder was something like a couple of minutes just to travel 1D in that vortex, to do this vortex motion that you see. It would take 3-4 minutes or something, you know. So a material caught in such a vortex, this Moffat vortex, it takes forever to come out, and it is likely to degrade. And I have published a paper in the PPS Journal of International Polymer Processing last year. Now, biggest problem in extrusion is probably the unmelted polymer at the end of the screw. Probably number one. Second, probably poorly mixed materials that I mentioned. And third, degradation that is possible. Well, give you an example of pipe extrusion. It was in Europe, a northern European country. The material was polypropylene, and the material was subjected, it was production of corrugated pipe, and the material was subjected to a compression test. We were trying to figure out where was the material coming from. We thought in the beginning that it was a problem with the resin. We took the resin, we measured, you know, and all that, you know, viscosity, tensile testing, passed all our university tests. However, in the plant test, you see, it was a compression test, it would fail. They have a standard, it's an ASTM standard, it would fail. Question is why? Well, back suspected the extruder. Why I suspected the extruder was that polypropylene does not melt as easily as Hdpe. I knew that the supplier of the extruder and the screw had a lot of experience with Hdpe, and I said, well, maybe these people think that they would use similar screw design. So I suspected that one. There was nothing unusual in the die. I checked the die. There was nothing there. And so I suspected, again, I said, probably I have trouble with the screw design itself, because what is known in industry in general is that polypropylene melts about 30% less than Hdpe under the same conditions. And I'm not really sure why. We did some work, might take another look at it, but I'm not quite sure why. But the net result is that polypropylene is rather difficult in melting. And so we wanted to see what really happens. And I did a computer simulation with my Extrusion software package. It was a very long screw, L/D 40. And I discovered that at the end of the screw, the software determines the melting, and you see at the start of the, under the hopper, you have 100% solid, and then we determined the width of the solid bed, and at the end, we had quite a bit, about 10% predicted unmelted material. But again, would they trust me? You know, I mean, in fact, the extruder manufacturer questioned the ability of my software, asking me about parameters, and some parameters, truly, I would have to guess. What is the friction coefficient between polypropylene barrels, pellets, and the barrel? Well, I guessed one. You know, did you ask me, did she measure it? No. Well, I said I guessed, I made a reasonable guess, all right? So we could not really convince. So I said, all right, we'll do something else. We had a pipe. We see nothing. Like we see a pipe coming out. Pipe is black. Because color said, okay, we're going to extrude polypropylene. And at the end, we're going to put a flat sheet die. Here it is. Well, take a look at it. I don't know, do you see it? What happens? Let me just come over there. Right? You see the angles? Okay? Well, my job was done, right there and then. I mean, we have, you see, we put a sheet die, just there was a small die, was maybe 10 inches, whatever, even less, I think. Maybe 15 centimeters, something like that. Thick sheet coming out. Material is unmelted. Well, if you have material like this, you're not going to make good pipe, all right? You're not going to make good pipe. And that was the problem. A new screw was designed, the problem was solved. Now, before we finish it for coffee, I have the simple example that I mentioned in the book, in which case, and I strongly urge anybody interested in extrusion to do this simple example. Okay, in which case we calculate an equation for the performance of the screw, another one for the die. Where they intersect is the operating point, and you get the output and the pressure. So very simple example. I said it, I go over in great detail, and in fact, I compare that to extruder simulation. We got very good results. And the results of the extruder simulation are like this. You can predict the pressure, you can predict the output, all the things that I talked about. And of course, with the extruder output, you can predict the temperature, you can predict the solid bed. Pretty much all you need for the design of an extruder, the design of a barrier screw. The problem that I have is that it is a difficult job. And it is a difficult job because I have poor information. Data are not very good. For example, I can measure viscosity, no problem. All right? But when you ask me, I need friction coefficients. And there are other questions. How do I know where the melting starts? I have to make some guesses. You know, we have a melting length or something like that in there. We have to make some guesses. So in a way, we have built a software package with which we can predict the performance of an extruder, including simple screws, barrier screws, screws with mixing elements, but we miss, we're short of very, very important information, data that is especially related to solid bed performance. Okay, with that, we are moving. The next thing is extrusion die design, which we will cover after the Hdpe we're going to have. Thank you. We will start in half an hour from now. That is